The elements, a visual exploration of every known atom in the universe. We are starting off with our exploration with dysprosium. Now, dysprosium. It's not that there isn't anything to do with dysprosium. It's a minor component in some alloys, in a terminal alloy, and which is discussed in the previous episode too. It can be optically be a minor component in the neodymium iron boron magnets to make them slightly stronger, but it's a minor component in several other applications. Practically, though, by itself, it's not a major component in almost anything. Himalayan sea salt is sold with claims that it's healthier to eat than regular salt, but mainly because it has a laundry list of elements, including dysprosium, which is not healthy to eat. So healthy eating that is kind of suspicious. Usually, if you go ahead and Google the element of a name that is naturally occurring and actually somewhat useful, you will usually find the companies going ahead and telling you what it's technically used for and how they use that element or something like that. But if you look up dysprosium and you have to go to the 4th page result before you find anything that isn't a periodic tables website entry for dysprosium, usually an obligatory that says it's an element, so we have a page about it, sort of page. But that doesn't mean there are no applications towards it. There are some important applications towards dysprosium too. It just means that people who know about them don't really feel about the need to really talk about them in public. Beyond the world of what you find on the internet, everything else is just on the scientific papers. And there is a whole lot of realm of the private knowledge that are kept secret by companies. Dysprosium, for example, is used in dysprosium iodide and dysprosium bromide salts to impart valuable spectral lines inside there as well too. Basically, you'll always use it as a salt, or you go ahead and use some cathode lamps to have some dysprosium containing them. Its atomic weight is 162.5, its density is 8.551, its atomic radius is 228 picometers, its crystal structure, it's a hexagonal prism more specifically. For F, it's almost there, just like 4 more to go, and it has a pretty low melting temperature, has an even lower boiling temperature at certain times. Next up, we have helium, number 67. Helium achieves the pinnacle aspirations of a rare earth element. All of them have some interesting magnetic property, but helium itself has the highest value of the most important one, particularly important one, the magnetic moment. When you go ahead and what this means, if you place helium inside a magnetic field, what you get is that all the helium atoms will line up with each other perfectly, and the magnetic lines of the force closer together. Like, you can bring the magnetic lines closer together, it will force them together, and you'll create absolute magnetism, which is really useful, and this is the most useful property of any rare earth element. Helium pole pieces can be used in MRI machines. MRI machines literally use magnets inside them anyway. And at the end of a magnet, you really get a stronger magnet if you add some helium to it. Practically what I'm trying to say is helium itself is only useful for magnets, except it is not only that. Helium chloride is in the form in which this element is inside the high-intensity version of the gas, where helium spectrum is kind of useful. And MRI machines use helium pieces to concentrate their magnetic field so that instead of like letting it wonking away and make sure that they won't be able to see only a hazy part of your brain, they will make sure that all the magnetic stuff will go into your brain so they can actually see it. Just make sure you don't have a mechanical heart, or else the heart will be ripped out and you will die immediately. Oh god. Speaking of medical applications, other than MRIs, you can even use them for lasers and laser surgery, such as the helium dome YAG, which is the yttrium, aluminum, garnet, and solid state lasers, which you really need if you really need to pierce something precisely what a scalpel won't do. Its atomic weight is 164.93032, its density is 8.795, its atomic radius is 226 picometers, and its crystal structure is a hexagonal prism. It has a pretty high melting point. It has a slightly higher melting point. For F, it's almost there, like 3 more spaces to fill. It has a really balanced atomic emission spectrum, although it is really, really hazy. Alright, next up we have erbium. This is number 68, erbium. Erbium plays a crucial role in modern communication systems, mainly because it allows pulses of light to be amplified in a fiber optic cable. You go ahead and use it in your laser-powered waveguide amplifier. You go ahead and basically you're creating light. You're creating fiber optic cables with erbium itself. It's a weak pulse of light coming down. Those optical light enters into a section that has a small impurity of erbium. which is introduced into the glass fiber. The pulse then exits this erbium doped version, see, with much brighter. It's basically AC current, but with light. You know, like AC DC, right? Alternating current. It's alternating current, but for light, not electrons. Erbium, however, has some of the bad things about it is that to operate this device, you have to know about the erbium doped fiber amplifier. You first need to pump energy into the doped fiber with a laser, which is really dangerous, and I highly recommend you don't do this at home, especially if you are a kid. The energy is stored inside these erbium atoms in the form of electrons promoted to the higher energy excited states, and the energy just stays trapped there until a pulse of just the right wavelength of light comes through and triggers all those electrons and light beams to decay back to their ground state and release their stored energy as light. It's really hard to use practically. You have to have the right frequency to make sure that it can become brighter. Yeah. Its atomic weight is 167.259, its density is 9.066, its atomic radius is 226 picometers, and its crystal structure is a hexagonal prism. And it has a pretty, oh man, it's so close to filling that gap up. It has a really balanced atomic emission spectrum, except it's missing a bit over here. It has a pretty high melting point, and it has a pretty low boiling point as well too. Alright, next up we have number 69, Thulium. Thulium itself, it's an interesting element. There's this guy who wrote Nature's Building Blocks named John Emsley, and he called thulium the least significant of the elements ever. Strong words there, but can someone stand up for thulium? It's just one more rare earth element, and it's really interchangeable. It's really significant in the sense that it's not significant at all. It's quite worthless. Thulium contributes to a critical broad range of green emission lines in metal halide lines, but other than that, there's not much else you can use for thulium. After its discovery in 1879, thulium remains so rare and so difficult to separate from the most abundant rare earth ores that, well, no, it wasn't until 80 years after it was discovered that you could buy it commercially. Even then, it became only available as an official way to separating all the rare earths having perfected. The solvent extraction method described under praseodymium, as I mentioned earlier, element 59, is using separate bulk quantities. Like, how you separate them is you go ahead and use a solvent to dissolve them away, and then you have to reform them, which is really a hassle too. Thulium is now at a reasonable price. Why else can element conductors get them at a reasonable price? And there's not much else we can really do about it. You can just use them for light, but other than that, nothing else really works. It has 168.93421 of atomic weight, its density is 9.321, its atomic radius is 222 picometers, and its crystal structure is a hexagonal prism. It has a medium high, moderately high boiling point, and it has an even slightly higher boiling point as well too. Finally, we're almost close to the end of 4F. I'm guessing that in the next element that it will be closed. It has a balanced version of the atomic emission spectrum. It's more leaning towards the left, or in this case down, so, but in this case we still have a little bit on the right. Next up, we have ytterbium. Ytterbium and yttrium, they're both used for lasers, just know that. Cities of Berkeley in California, Dubna in Russia, and Darmstadt in Germany went ahead, had to work on yttrium. They worked very hard to get their names named after them. Why else did they get Darmstadium, Germanium, or Dubnium? In fact, each of them had to make their own elements from scratch inside particle accelerators, which is really expensive to do, so, yeah, you know what? And, you know what? All of them are pathetically short-lived elements. They're not even natural, but you don't even really have any use for them. If you can somehow find them naturally occurring in some other part of the universe, which I'm pretty sure we'll find someday in like the next billion years, you're not going to have any practical use for them. Unfortunately, though, for them, they are usurped by ytterbium, which was created in this little town, Ytterby, this little city, Ytterby in Sweden, and it has practical applications and is long-lasting. High purity ytterbium bromide. It's used in the lighting industry, and there are so many other uses for it too. Ytterbium's star application is in doping agent in lasers. You use them in lasers, where it creates a color center, and it centers all that laser energy into one place, so you can concentrate it and shoot them out at the same time to make it more accurate as well too. That's pretty much one of the only applications for ytterbium, though. It at least has an application and it's named after one of their own places. Now, I really wish I could go ahead and explain to you how lasers work in a few paragraphs, but it takes years of algebra and calculus to at least understand how lasers work. The answer is worth it though. It has an atomic weight of 173.04, its density is 6.570, its atomic radius is 222 picometers, its crystal structure, it's a very stable cube. It's finally filled the 4F. I'm really happy about that. My satisfaction is there, and now we just have to fill the others. It has a very, very dotted amount of atomic emission spectrum, an extremely low melting point, at least for metal's case, and a slightly higher boiling point as well too. Most of the time at higher temperatures, it's a gas. And that's it for today. That is the end of the elements video for today. I'll see you guys soon for element 71. Until then, on out. Peace. Bye-bye.